Good morning, afternoon, and evening. How y'all doing today? Welcome back to Mr. Morrow's Algebra 2 class. Today, guys, we're going to wrap up the first half of this chapter, and we're going to learn how to add and subtract radical expressions. And it's kind of easy, okay? Bless you. Adding radicals is almost identical to radding terms, okay? To radding, I don't know what that meant. To adding terms. I'm thinking radicals, to adding terms. If you remember, guys, you cannot add any terms together just randomly. You have to add like terms. So, for example, if I had 5x cubed plus 3x cubes, that would be 8x cubes because the variables were the same and raised to the same power. Those were like terms, okay? Today we're learning about like radicals, and very similar to the like terms, like radicals are radicals expressions that have the same index and radicand. Now remember, guys, if you don't know your vocabulary, this is already where it's hurting you. Please remember that when you have a radical, okay, the n here, that's my index. The radical itself is the radical sign, and the stuff inside of the radical is called the radicand. Okay, so please be careful. So in order for you to add like radicals, you have to have the same radicand, and you have to have the same index. Okay, same thing. So for example, let's simplify each radical expression. All right, here you got 3 square roots of 5x minus 2 square roots of 5x. Pretty simple. This is going to equal 1 square root of 5x. Remember that there is an invisible 1 there. Okay, nice and easy. Yes, sir. No, that 1 is totally not needed. I just said remember, because for whatever reason, a lot of my students forget that there is an imaginary 1 there, Thank you, sir. For B, I unfortunately cannot add these. Not only are the square root of 7 and the square root of 5 not the same radicand, they have the same index, but they're not the same radicand. But not only that, but also, even if they were, I can't add the x squared and an x. So this was not a like term by many, many different reasons. C, I got 12 cube root of 7xy minus 8 cube root of 7x, fifth root of 7xy. Do these guys have the same radical? Do they have no, they have different indexes, guys, exactly. Do they have the same radicand? Yes, they can. Yes, they are. Okay, now, you technically cannot add these yet. All right. What can I do, though, here? Since they have the same base, can anyone think of a way to manipulate this to make this work? Yes. You're perfect. Okay, perfect. What my boy said was, let's think about the least common multiple. So that tells me that he knows that this is, I love it when that happens. He knows that what happens here is this is a 12 times 7xy to the 1/3, correct? And this is minus 8 times 7xy to the 1/5. All right? You with me here, guys? All right. What's the common denominator between 3 and 5? 15. So this can go to a 15, and that goes to a 5. That goes to a 15. That goes to a 3. So this would be 12 times the 15th root of 7xy to the 5th power minus 8 15th root of 7xy to the third power. Okay. Now, would I be able to add these though? Still no. The only reason I wanted to show you this, guys, is there's no way around this rule for adding. When you're multiplying them, you could get around the rule of them having to be the same index, because I can change the index, just like my boy said, by finding the common multiple. But when you're adding them, there's no way to get around this. But very good thought. I'm really proud of you for knowing how to go from the radical to the exponent. Very good. So when you're adding, there's no way to do it if they don't have the same radical, or rather the same index and the exact same radicand. You cannot add them. So here you would put not possible. Please do not put not real. It is a real situation. It's just not possible. Yes, sir. Yeah, for B as well would be not possible. Thank you, my brother. Thank you very much, kid. Okay, how about this one? 17 fifth root of 3x squared minus 15 fifth root of 3x squared. Can we add those? Absolutely. They have the same index and they have the same radicand. So this is 2 fifth root of 3x squared. Does that make sense, guys? Pretty simple, right? Not too bad? All right. How about this bad boy? 5 cube roots of x plus 3 plus 15 cube roots of x plus 3. Can we add these together? Do they have the same index? Do they have the same radicand? So absolutely. So in total, I have 20 cube roots of x plus 3. We're just adding the coefficients because this is just like adding like terms. It's like adding 3x plus 4x. That's 7x's. You keep the like term part and you add the coefficients. May we continue, brothers? Okay, now, it's not always going to be nice and easy like that. Sometimes, most of the time, actually, this is the way it's going to be. What is the simplest form of each expression? Now, you may look at this right off the bat and say square root of 12 plus square root of 75 minus square root of 3. Oh, this is easy, Moro. You cannot add these. Yes, you can. Before you start adding, you have to always try to simplify, okay? Now, you may say, Moro, you just told us you can't do anything. You're right. In a situation like this, right here, this guy, you're right. I did not have the same index, so if right off the bat, I can't do anything. It's not going to work. However, here, I do have the same index. Now it's our responsibility to see if we can break it down so that we can have the same radicand. Exactly. So you had your hand on my brother. What do you want me to do? How do I break this up, kid? Close. I know you're trying. I'm proud of you. This is 4 times 3. So this would be a 2 square root of 3. Did you say 3 square root of 3 because you... Yeah, no, that is 4 and 3. Thank you. Good job, kid. Now here, how can I break this bad boy down? No. Thank you. Good job. 25 times 3. What's the square root of 25? So now we have a 5 square root of 3 minus the square root of 3. Guess what, guys? Now I have converted these to like radicals. They have the same index and they have the same radicand. So 2 square roots of 3 plus 5 square roots of 3 minus the square root of 3 would be 6 square roots of 3. So before you add or subtract, before you just give up and say, oh, you can't do it, simplify the radical first. If the indexes are not correct, forget it. Don't even worry about it, y'all. Don't even sweat it. But if the indexes are the same, you got to simplify and see if you can. So for example, cube root of 250 is 25 times 10. So that's 5 times the cube root of 10 plus, what do you think 54 can be broken down to? Nice and easy. Think perfect cubes, think perfect cubes. Think perfect cubes. Think perfect cubes. Good job, guys. 2 and 27. Cube root of 27? Yes, exactly, guys. 3. Good job. Good job. So you got 3 and you got the cube root of 2 left over. Okay. Okay, can't do much with that. And then minus, what's the cube root of 16? No. It's 8 times 2. So you take out a 2 with a cube root of 2 left over. Because the cube root of 8 is 2. So, okay, so, yes, sir. Wait. This is completely wrong. No, I'm I'm a fool. I was doing a square root and it's a cube root. 100%. Thank you, kid. 125 times 2. Yes, this is 5 square root of 2, a cube root of 2. Yes, thank you. So now they're all like radicals. They're all cube roots of 2. So 5 of them plus 3 of them minus 2 of them. We've got 6 cube roots of 2. Make sense? Pretty simple, right? But you got to know how to break them down. Okay, 14 times the square root of 20 minus square root of 125. Okay, 20. Think perfect squares. What does that break up into? Yeah, 4 and 5. What's square root of 4? Yeah, so this is going to be 28 square root of 5. How about this bad boy over here? 25 and 5. So square root of 25 is 5. Square root of 5. So what's 28 square root of 5 minus 5 square root of 5? 23 square root of 5. Very good. Beautiful, guys. D, 4th root of 32 plus the 4th root of 48. Let's see if we can do anything here. I'm going to break this up into 16 times 2 because the 4th root of 16 is 2. Right? 2, 4, 8, 16. So I've got bless you. 2, bless you. Times the 4th root of 2. Plus, can 16 go into 48? Yeah, 3 times. And the 4th root of 16 we already determined was 2. So this is 2 times the 4th root of 3. So we simplified it. It's real pretty and all, but we can't do anything with those except for simplify them, and we're done. But moral, we have the same index. Yes, but do we have the same radicand? No. Yes, sir. Yes, on a test, leave it like that, please. Just like this. Because that tells me you knew how to simplify it. You knew the procedure. You knew that you had to check and simplify first before you added. So that shows me you understood. Thank you so much, kid. Great question. Here. How can I break down 54, guys? Thinking cubes here. Cubes. Yes, nice job. Nice job, brother. 2 and 27, y'all. So I got, what's the cube root of 27? So I got negative 15, okay, x, and then I have a cube root of 2x left over, plus 7. Can I take the cube root of x to the 4th here? Yes, sir? No, the x would not be absolute value because the absolute value only happens when you take an odd out of an even. Here you're taking an odd out of an odd. Thank you so much for caring, though. So, guys, what's the cube root of x to the 4th? How many times is 3 going to 4? 1 time. What's left over? A cube root of 2x. Now, are they like radicals? Okay, so that's going to be negative 8x times a cube root of 2x. Yes, sir. Where did I get the negative 15x? Thank you so much for asking, my brother. What's the cube root of 27, sir? 3 times negative 5? No, thank you, my brother. Thanks for your honesty, kid. Talk to me, guys. Questions, comments, concerns, problems, issues. We got plenty of time. Plenty of time. Sir, talk to me. Correct. The 20 is 4 times 5. Square root of 4 is 2. 2 times 14 is 28. Thank you so much for your honesty, kid. You had a question, my brother. Well, I'm simplifying. I'm simplifying. I'm taking out any square or cube or 4th root that I can. I'm taking anything out, and then I'm leaving the leftovers. If those leftovers happen to be like radicals, then we add them. And like radicals are only like radicals when they have the same index and they have the same radicand, which is that inside part. Cool? Thank you, my brother. Anything else, guys, before I continue? Thank you for your honesty. Yes, sir. What letter, sir? E. Okay. Yes, sir. Okay, well, I have the cube root of x to the fourth. Well, this x was already here, my brother. And this x was already here. I wouldn't divide it because I can't take an x out of here. Do I have three x's to take one out? No. But here, the cube root of x to the fourth. How many x's do I have there, bro? So 3 goes into 4. How many times? One time. That's why I have one x that came out. And what's left over, sir? 1. That's why I have one x inside. That's my remainder. Does that make sense, my brother? Thank you so much. I really appreciate your honesty. Anything else, boys, before I continue? Thank you. Okay, thanks a lot, guys. Now, when a radical appears as a denominator of a quotient, guys, you must convert the quotient so that the denominator does not contain any radicals. This process is called rationalizing the denominator. This is huge, really important. Remember when I told you anytime you see a radical in the denominator, remember that I told you guys that's illegal for right now? Remember I said this was coming. Well, here it is. In order to rationalize the denominator containing a single square root, simply multiply both the numerator and the denominator by the square given in the denominator. So, for example, and this should be for the square root given in the denominator. One thing you must remember, when I have the square root of a times the square root of a, in other words, the square root of something times the square root of itself, it's always going to equal itself, the radicand pure and simple. Why? Because if I take the square root of a times the square root of a, I get the square root of a squared. And what's the square root of a squared, guys? A. So anytime I multiply a square root times its exact replica, my answer will be the radicand. So square root of 5 times square root of 5 will equal 5. If you don't believe me, do it the long way. Square root of 5 and square root of 5 is square root of 25. Square root of 25 is 5. Square root of 3xw times the square root of 3xw is 3xw. Okay? Anytime you multiply a square root times its exact replica, the square root disappears and the answer is the radicand. Yes, sir, my brother. Yes, sir. I'm going to show you right now how that works. But they would combine because you're going to multiply them. Okay, so now, we're rationalizing, okay, just with square roots. This is going to get more complicated. But I want to do baby steps with you, okay? I know that in the homework there's a few questions like this, and they didn't really do very good job of teaching it in the chapter, in the section. So I went ahead and added a few notes just so you can understand. All of these here, guys, these are technically, mathematically speaking, illegal. You are not allowed to have radicals in the denominator, period. Now, this is the easiest of rationalizing because we're just dealing with square roots. We're going to get to cube roots and nth roots later on. But right here, I have 2 over the square root of 5. My brothers, I cannot have the square root of 5 down here. So in order to get rid of the square root of 5, I need to multiply a square root of 5 to both top and bottom, to both the numerator and denominator. Now you may think, why is that going to help anything? But let's think about it. I got 2 now times the square root of 5 over, what property did we just learn? What's the square root of 5 times the square root of 5? 5, done. If you ever forget that, guys, remember, square root of 5 times square root of 5 is square root of 25, because you can multiply the insides. And the square root of 25 is 5. Bing, bang, boom, I'm done. Square root of 7 over the square root of 12. I cannot have a square root of 12 in the denominator. So I'm going to multiply square root of 12 to both top and bottom. So I'm going to get the square root of 84 over 12. And now the square root of 84, I may or may not be able to simplify it. I don't know. This is going to be 4 times 21, right? Okay, 4 is a perfect square, right? So this comes out as 2 times the square root of 21 over 12, which I can reduce square root of 21 over 6 before I continue. Do you see what it is to rationalize? For now, when you just have a square root in the denominator. Again, guys, we got plenty of time. We got plenty of time. Plenty of time here. Talk to me. Sir, my brother, thank you. No, you cannot leave it as square root of 84 over 12, sir, because we got to simplify, because they'll never give it to you like that in an SAT or an ACT, or a professor will never give it to you. Sorry, brother. Thank you. Yes, sir, you had a question, my man? You cannot divide radicals and whole numbers. You cannot multiply radicals and whole numbers. You cannot add radicals and whole numbers. You can only add like radicals. We're going to talk about multiplying and dividing soon, right? Because we haven't done that yet, right? Yeah, next section is multiplying. And then we'll talk about dividing them later. But no, you cannot. You can only add like radicals right now. And for multiplying, you can only multiply radicals that have the same index. But we'll get to that soon enough. Right here, I've got 4 over 5 square root of 2x. I cannot have a radical in the denominator. I just can't have it. So I must multiply square root of 2x to both top and bottom. So I've got 4 square root of 2x over square root of 2x and square root of 2x is what, guys? 2x times 5, 10x, reduce it, 5 square root of 2x over 2x. I took out the 5. Yeah. And very tempting, but you cannot get rid of those x's, because one of those x's is outside of a radical, the other one is inside a radical, and you can't do that. Yes, sir, my brother. Okay, that's going to come later, but since you're asking, the question was, if I had a square root of 2x up here, and I had a square root of x down here, what would you do? Well, the law is that you can multiply and divide radicals with the same index. So this would actually become one big fat square root of 2x over x, which would then become square root of 2 because the x's would cancel. That's where we're going. That's coming soon. Great question, though. Does that make sense, though, guys, for rationalizing? Nice and easy stuff. Promise? Okay, now, how do we do this, guys? We already learned how to add radicals. Let's go ahead and see an SAT or an ACT application. I want to find the perimeter, okay? So, how do we do this? Add them up. Thank you. Perimeter is the sum of all sides, guys. And we know already that we can only add like radicals. So what would my answer here be, my brothers? Yes, 4 radical square root of x plus square root of 10x. Bada bing, bada boom, that's it. Moro, why can't you add more? Because I don't have like radicals anymore. I have 2 radicals with the same index. Yeah. But they don't have the same radicand. Does that make sense, gentlemen? Yes, sir. Okay, that's a beautiful question. Let's do it. If, let's say they tell you, wow, this would be kind of weird to do it like that, but let's just see. If they told you to apply the Pythagorean theorem here, this would be the square root of x squared plus 3 times, plus square root of 10x squared equals 3 times the square root of x squared. If they wanted to solve for x here, my brother, what's the square root of x squared? Plus, what's the square root of 10x squared? Equals, what's 3 square root of x squared? 9x, right? So this would be 11x equals 9x. So x is going to equal 0 here at the end, but yeah, this is what you would do divided by 2. So this doesn't work, this doesn't exist, but you asked, put into the Pythagorean theorem, that's what it would be. Because a square cancels out a square root. Thanks, kid. Anything else, boys? All right, let's do this. Let's do the application. Thank you very much. Hope you learned a lot. God bless you. Bye-bye.